All right, so last time we were discussing some of the characteristics of photoelectric effect, right? We talked about why not all electromagnetic radiations are capable of producing this effect. What is required to produce this effect? That's where we discussed what's called the threshold frequency and some other characteristics such as one electron can only absorb one photon at a time. So it means there is a one-to-one relation in there, and that the fact that there is no time delay between this absorption of photon and emission of an electron. It happens instantly, right? With that, we moved on and we talked about this total energy for this entire effect, and that was the sum of the work function of the material and the kinetic energy of the electron that is emitted. And so that's also where we discussed this idea of electron volts, which is just a unit of energy, which tells you that this is the amount of energy gained by an electron when it moves through a potential difference of 1 volt. So this much energy it will gain. So from there, we discussed what's called the photoelectric current, and we'll see its dependence on the frequency of the electromagnetic radiation as well. So any questions from that class?
Sir, the photoelectric current last part was not clear.
Okay, I'll explain the photoelectric current thing again. Just a second. Okay, so photoelectric current is again when you have this, you throw the radiation onto the metallic surface. What happens is it emits electrons. For one photon, there's one electron. So if you throw a beam of light, which is thousands and millions of photons, for every one photon, it will throw out one electron at a time. So which means that eventually you'll have a lot of electrons coming out of the material. That is, electrons are just charges which are moving. So moving electrons are producing some current. For the sake of this argument that we're talking about the photoelectric effect, we'll call it the photoelectric current. So it is the rate of emission of electrons from the surface of the material during this photoelectric effect. Then I said that if I increase the current, then I would have an increase in number of electrons per unit time, right? Because what is current? Current is the number of charges, or in this case, electrons, moving through something per unit time, right? So if I increase the current, then I'm increasing the number of electrons that are flowing through some thing per unit time. And so the opposite of this is also true. If I decrease the photoelectric current, then less electrons would be leaving the metallic surface per unit time or per second, right? So then the thing that I wanted to explain is the effect of frequency of on this, right? So again, what I had in this thing was that I increase the frequency of the radiation. What would happen? So what would happen to the photoelectric current if I increase the frequency of radiation? What do you think? What effect should be there on the current? Okay, it increasing the frequency, which is just one over the time period, right? So it is total number of, or you can say oscillations per unit time, but that increase in frequency is not affecting the total number of photons per unit time, right? Which was the photoelectric current. So increasing the frequency has no effect on the photoelectric current. Whether I increase it, decrease it, photoelectric current stays the same because the number of photons that are incident per unit time on the metallic surface are same, right? So the total number of electrons that will be emitted are also the same. So hence, frequency plays no role in the changes on photoelectric current. So is that clear?
Yes, sir.
Okay.
So
So
the
if
electron would remain the same. No change on electrons also.
sorry, can you repeat?
No change on electrons also. They would remain same.
If I increase the frequency, right? Yeah, they would be the same because the number we're talking about the number of electrons, right? So that they would be the same. If you that's what you mean by no change on electron,
Yes, sir.
right? Because I mean, obviously, electron is fundamental particle. You cannot really change the electron. So in this case, the number of electrons are not changing, right? Okay, so if I increase this frequency of the electromagnetic radiation, it has no effect on photoelectric current because I'll just call it photocurrent for this thing, and that's because the number of photons, or you can, so the number of photons incident stays the same, so the number of electrons emitted is same. So that's why, but in, current is this number of electrons per unit time, right? I mean, is the same, you should also say per unit time, right? So that's why there is no increase in the frequency of this. There is no increase in the photoelectric current due to the change in frequency. Okay, so now let's see how does that look like. I need some space on this page itself, so let's make it. Okay, so this now let's make a graph just over here. On this axis, we'll take this photoelectric current. It's the current is not so big. It is in milliamperes, right? So and on this axis, let's take frequency, right, which is in hertz. Okay, so what kind of a graph would you expect? I'll also tell you that there is the threshold frequency for a particular material is over here, F naught. So that this is the threshold frequency. Okay, tell me what would happen to the current until or before I reach the threshold frequency. What should the graph of current look like for that?
Straight line.
A straight line where? At some value or at zero?
At a value.
Okay, but okay, so again, try to recall what is threshold frequency. It is the frequency after or at which photoelectric effect happens. At that frequency of radiation, electrons will be emitted. Before that, no electrons are being emitted. So before that, no electrons are being emitted. That means before that, no current should be there, right? There is no electrons flowing per unit time. So there would be the current until threshold frequency would remain zero. So is that clear?
Yes, sir.
Okay, so I'll pick another color and let's draw a line over here. Okay, so this color, you can see there is no current, and as soon as you reach the F naught, you will not expect the current to increase in this way. You will expect an instantaneous increase in the current because there is no time delay between the absorption of photon and emission of an electron. So what would happen is instantly you would have some value for the current, and that value will remain constant. Why constant? Can anyone tell me that? Why did I draw a straight line like this? Why not a vertical line, or I mean, why not a y equals x line or some curve or anything? Why did I specifically drew straight line?
The
Because increasing
frequency.
frequency wouldn't have effect on the current.
On the photoelectric current. Yes, exactly. Right. So as we just saw that the increase in frequency has no effect at all on the number of electrons per unit time. So the current stays constant whether I increase the frequency or not. Okay, so let's come back to our equation, which was this. Let's go to the next page. Okay, I think here. Okay, so so the equation was for the photoelectric effect. Let me change the color back. Was the total energy is equal to the work function of the material plus the maximum kinetic energy of the electrons, right? So suppose that I want to see visually see how does the kinetic energy of an electron that comes out, right? So we are interested in that. So this is ek maximum, and this is the frequency, right? So let's see how we want to see how does the kinetic energy of the electron changes as we increase the frequency. So what we'll do is we'll say that this equation looks familiar to this one. Y is equal to mx plus c. Acha, before that, we take some values for some frequency and check the kinetic energy of the electrons experimentally, and we see that with the graph we expect looks something like this. A straight line that does not pass through the origin but at some value. Acha, why do you think we should already expect that it should start from this some other point and not zero? Why should we expect this a graph between the kinetic energy and the frequency of the radiation to not start from zero again? Anyone?
At zero frequency, there would still be some kinetic energy.
Okay, yes, at zero frequency there will be some energy. Okay, but why at this point you should expect the kinetic energy to be zero up until this point? I mean, so you see what's happening is at this point the kinetic energy is zero. Again, that is simply because this is that particular frequency after which you see something happening, right? So this frequency is then called the threshold frequency, and that's why you would expect the line to pass through some intercept, right? X and Y intercept. And then you can see that if you look at these equations and relate them for a straight line, it immediately tells you that, well, we have to rearrange the first one because on the y-axis we have kinetic energy, so we want that our variable, dependent variable, and then you have ek would be E minus phi. So now let's compare these two. So when you compare these two, you clearly see that the gradient of this line, ek equals e minus phi, the gradient is equal to well, it is equal to some constant, right? And that constant is before I say that, let me just clear this up even more. This is ek equals e. What was e, right? E is, because again our relationship is, we're checking with f, right? So where is f in this equation? It's nowhere to be seen, but it's hidden inside this e, and that is hf. E was equal to hf minus phi. Phi is also hf, but hf naught, right? So this f naught is a fixed parameter, is a fixed constant, fixed frequency for a given material. So we don't have to open that. That f naught will have no effect on this frequency. So this is our equation. In this, you see that the gradient, let me write down as this, gradient of this line is h, because f is this axis, right? So compare this y equals mx. So x is f here, y is ek. So whatever is with x, as in whatever is with f, is the gradient, and then the y-intercept is the work function, or the negative of the work function. And so you see that this satisfies this graph. Okay, so any questions from this?
No, sir.
Okay. So let's move on to the next one. Let's talk about the increasing intensity, right? So suppose now if I increase intensity of the radiation, intensity of EM radiation. Okay, again, this is done independently, which means that frequency is still the same. You do not do anything to frequency. Frequency is fixed. You don't change it, right? Keeping the frequency constant, same. Okay, so first of all, what is intensity of electromagnetic radiation? What do we mean by that? Intensity of EM radiation. Can anyone take a guess? What do we mean by when we say the intensity of electromagnetic radiation?
How strong the radiation is?
Okay, but on what does that depend?
Amplitude over power?
Yes, okay. So that means amplitude is the energy transmitted, right? So the higher the amplitude, the higher the energy is transmitted per unit area, right? So that is what your amplitude defines. And then it is per unit time. So this is really the intensity in this, when we're talking about particles, right? So we'll, or electrons, charges. So we'll say that intensity of electromagnetic radiation is the energy, the amount of energy that is transmitted per unit some area, and then all of this per unit time divided by time, right? So this is E over T divided by, sorry, not E over T, E over A divided by T. Acha. So this is my intensity. Now, what does this imply? Energy transmitted per unit area. Remember, one photon carries some energy. Then you can have multiple copies of this photon, as in multiple photons. So okay, let's ignore this one for a bit. The first one that I drew, that is over there, you can see it has some energy E, right? Let's deal with this. It has some energy E. How can I increase this energy E? Suppose I do not disturb the frequency. I cannot change the frequency of this photon. What other way is there to increase this energy of the system? Of course, you could say you could increase the frequency, and so the energy would increase because E equals HF. But I'm saying that let's keep frequency constant. Can we still increase the energy of the system? Anyone? Okay. So what we can do is we can bring another photon that has some energy E. Now, this total system combined together carries some energy 2E, right? So that's how I'm increasing the intensity of the system, by adding more photons to the game. And so what does that mean? That means that intensity is corresponds to the number of photons per unit time. Okay, so how can I increase intensity then? Anyone? How can you increase the intensity?
Decreasing the time or increasing the area.
Okay, but let's suppose that that remains the same. What else can I do? Suppose the area, your surface is not changing its area, right? It's fixed for a particular material. So what else can I do?
By increasing the frequency?
By increasing the frequency, yes, very, very true. But again, we are saying that let's keep the frequency fixed, right? Let's not change that. Is there any other way?
By
Yeah.
increasing current?
By increasing the current, which means really by increasing the number of photons that are incident. And if for every photon that is incident, you will have a current, right? An electron produced. So yeah, in one way that is very true. But let's frame it even more basically, as you can increase the intensity by increasing the number of photons, because the photons are in our control, right? So you're throwing that laser, you're throwing the beam, you can control how many photons you want to throw at the metal surface. Whatever happens then, the electrons being ejected out, that is physics in play. That's what is happening because of the laws of physics. And so you can control the intensity of the photons. So that's why we talked in terms of what we can control, right? So that's why you increase the intensity by increasing the number of photons. So yeah. Now, what about what effect do you think would it have on the photoelectric current? Effect on. What do you think? What should happen to this current?
Increase.
Okay, yes. But why?
The energy is increasing. The photons are
The number of photons are increasing, right? So if the number of photons are increasing, for one photon corresponds to one electron thrown out. So that means if I increase the number of photons, more electrons will be thrown out per unit time. So the current then increases, right? So it increases as the number of photons increase, which implies number of electrons increased, as for one photon corresponds to one electron ejected. Okay, so is that clear?
yes, sir.
All right. Okay, so let's again see visually the graph of this thing. Suppose here I have my intensity. I cannot use I because I used it for current, I think. So let's just write intensity. And here we have our photoelectric current. Okay, so what do you expect the graph to look like? So what we are seeing is, as I'm increasing the intensity from 0, what effect does it have on the current?
It increases.
It will increase. Would you expect it to increase linearly? For every change in intensity, you'd have a similar change in the current.
Yeah, I
As
think
in, yeah, it would be, because again, for every single photon that corresponds to intensity, every single photon, one electron is released. Because of this one-to-one relationship, you'd expect a straight line, y equals x type of graph, right? So if this is your 0, this is I, this is intensity, this is how the graph looks like. Okay. So now let's see, if I increase the frequency of electromagnetic radiation, keeping intensity fixed, what would happen to, let's talk about the photoelectric current, sorry, the kinetic energy. What would you expect to happen to the kinetic energy if you increase the frequency of the electromagnetic radiation? This energy of the electrons, right? Okay, so I expected that you would immediately say that it would increase, and also that would be correct, but it comes from this thing that we have E is equal to, what was the equation? E is equal to
HF.
the work function, yes, plus the kinetic energy, right? So if this is your equation, right, and what you're doing is you're increasing the frequency. So HF is equal to phi plus EK. This frequency is being increased. What would happen to the maximum kinetic energy? Remember, work function is for a particular material. So I'm not changing the material. Material is still the same. So phi is fixed. Then how will it cater for the increase in frequency? It will increase the kinetic energy of the electrons that are emitted. So you would expect it to increase because you can say that the work function phi is fixed. Okay, so is that clear?
Yes,
Yes,
sir.
sir.
Okay. What about the photoelectric current? Again, what would happen to the photoelectric current if I increase the frequency of the electromagnetic waves or radiation?
It should stay constant.
Okay, what does this increase in frequency does to the intensity? Okay, it would stay constant as long as you keep this intensity fixed by some means. But suppose you started the experiment with a fixed amount of intensity and you do not change it. But whatever you do to frequency can have some effect on intensity. So you're not changing it physically, but in the experiment, as the frequency is increasing, it can change the intensity. So let's say that is happening. That's what's happening. The intensity changes because of the increase in frequency. Initially, you do not change it. You do not do anything to the intensity. It just changes because the frequency is changing. So by increasing the frequency, we are also it would cause the intensity of the electromagnetic radiation to be fixed. To be increased. But again, coming back to our point, we want the frequency to remain constant. So to keep the intensity constant, as in to keep the frequency constant, that would correspond to the constancy of the intensity, the number of photons will decrease. And that's how it will cater for keeping the intensity fixed and not changing it as I increase the frequency. So if I decrease the number of photons that are reaching this surface, I can somehow maintain this constant intensity. Right? So the number of electrons emitted will decrease because the photons have decreased. And for one photon, one electron is there, right? So photoelectric current would decrease. So is that clear?
Yes.
Okay. So to do that, number of photons decreases. Okay. So the number of photons decreases, which implies decrease in photoelectric current. Okay, so that concludes our topic of photoelectric effect. In the next one, we'll start the idea of that light is not a wave. How is this effect responsible for saying that the wave nature of light is not really true, or it rejects the idea of the wave nature of light.
Sir, don't we have the momentum of protons left?
Sorry?
Don't we have the momentum of photons? Isn't that another topic, or isn't it?
The momentum of photons is this kinetic energy of the photons, right? This energy corresponds because kinetic is this, the energy is p squared by 2m. This is really how the kinetic energy is written, right? So p, this carries m squared v squared divided by 2m. So m goes, so this gives you m v squared by 2. This is where you get this formula from. It is originally, this is the real equation, right?